In this video, we take a look at some inverse problems associated with the normal distribution. Our first task is to find the value of the random variable such that the probability of x being less than that value is equal to 0.504. Given the symmetric nature of the normal distribution, a probability value of greater than 0.5 means that we must have situations such as shown in this quick sketch. The shaded region has an area equal to 0.504. Being greater than 0.5, a value of x must sit to the right of the mean. Now we're going to use our cumulative normal distribution table to solve this problem. And to do that, I'm going to have to transform things to a standard form or normalized form because my table is in the standard normal distribution form. So first of all, instead of considering x being less than x, I'm going to be talking about the probability of z less than some specific value of the standard normal variable. While I've transformed from x to z, it doesn't make any difference to the probability value itself. So what I'm going to do is go to my cumulative normal distribution table and try to find where 0.504 is on that table. So this time, instead of looking up values of z, because I don't know z, I need to look within the table itself because I'm given a probability value. 0.5 is right up here at the start. 0.504 must be pretty close to that. So if we look around this region, you can see that there it is right there. So a probability value of 0.504 corresponds with a z value of 0.01. So moving back to our working, we can write a probability of 0.504 corresponds with a z value of z equal to 0.01. Now that's a good start. We've figured out the z value, but what I'm actually looking for is the corresponding x value. Now remember that to transform or normalize random variables, we know that z is equal to x minus mu over sigma. Here I have the z value, 0.01, and that's going to be equal to the x value we're looking for minus mu, which is 22, given in the problem, and sigma, which is 2.75, also given in the problem. Now I can simply rearrange this equation to solve for x. Multiplying both sides by 2.75, I get 0.01 multiplied by 2.75 is equal to x minus 22. And finally, 0.01 multiplied by 2.75 plus 22 is going to be equal to my x. If we evaluate this and switch sides just to make it neater, we find that x is equal to 22.0275. So an x value of 22.0275 is the value we need such to find that the probability of x less than small x is going to be 0.504. In part B, we're looking at an x greater than situation. But again, we're trying to find the value of the random variable that gives rise to a particular probability. So again, at one stage, we're going to be looking up the inside of the standard normal distribution table. Let's start with a quick sketch. A usual bell-shaped curve for the normal distribution. Again, we have a mean of 22. Probability value that we're given is less than 0.5, less than half of the probability. And we're looking for greater than an x value. So we're going to jump over to the right of the mean. We have some x value here, little x, and the probability that we're given is for x is greater than that number. That's 0.3707. We can start by noting that we're looking at the probability of x greater than little x, and that's going to be equal to 0.3707, but our tables deal in x being less than certain numbers. So I'm going to turn this around to 1 minus the probability that x is less than lowercase x is equal to 0.3707. In other words, the unshaded region over here is equal to 0.3707. That is when it's subtracted from the entire probability. Now, rearranging this, we can write that the probability that x is less than lowercase x is equal to 1 minus 0.3707, or 0.6293. Now we're back to pretty much the same problem as we had in part A. So we need to think about standardized values and looking at the standard normal distributions, cumulative normal distribution table. And what that comes down to is asking ourselves this question. What is the lowercase z value for which the probability that capital Z is less than lowercase z is equal to 0.6293? And to answer that, we go to our cumulative normal distribution table and search in the interior for that value, 0.6293. Looking through the table until we get to about 0.6293, there it is right there at the intersection of 0.3 and 0.03. So the Z value we're looking at is 0.33. So the table indicates that lowercase z is equal to 0.33. Just as we did in part A, we're not looking for a z value, we want to get the x value. So we need to undo the transformation. Remember, x minus mu over sigma. For us, we have z equal to 0.33, and that's going to be equal to x minus 22 over 2.75. And we can rearrange that equation to solve for x. So we have 0.33 multiplied by 2.75 plus 22 will be equal to x. Evaluating those, we get that x is going to be equal to 22.9075. So the probability that x is greater than 22.9075 is equal to 0.3707. In part C, we're trying to find what is x such that the probability that our random variable is less than that x value is equal to 0.3. Now visually, that looks like this little sketch here. We've got some unknown x value, and the probability that our random variable is less than that, shaded region, is equal to 0.3. The table that we're working with doesn't allow us to work with values less than the mean. We only have a table for values greater than the mean. So we need to do a little bit of working around here with our variable. First thing I'll do is note that because of the symmetry of the normal distribution, there's a value on the other side of the mean, which I'm going to refer to as y, such that the probability that our random variable is greater than that y is also equal to 0.3. So what I'll do then is write down that the probability that our random variable is greater than y is equal to 0.3. Now noting that the entire probability or the entire area under the curve must be equal to 1, this black shaded region here, probability that x is greater than y, will be equal to 1 minus the remaining probability that x is less than y. So 1 minus the probability that x is less than y is also equal to 0.3. Now this I can rearrange to write the probability that our random variable is less than y is going to be 1 minus 0.3, or 0.7. So now we're in a sort of a situation where we can, once we standardize, look at our cumulative normal distribution table. That'll allow us to figure out the normalized version of this y value. Once we have the normalized value for y, we'll be able to then move on to obtain x. So at this point, we're asking the question, what is the z value in the cumulative normal distribution table such that the probability is equal to 0.7? So we go to our table, and we're looking for a 0.7 in the center here. Now, the closest we can get is these two values here. And they're both roughly either side of 0.7. So what I'm going to do is split the difference. So it's not going to be 0.52 or 0.53. I'm going to take 0.525. So jumping back, I'm going to say that Z is equal to 0.52. Now remember that that's the standardized version or normalized version of Y. So we have Z is equal to Y minus mu over sigma. And substituting the values, we know 0.525 is going to be equal to Y minus 22 divided by 2.75. We can rearrange that equation to get Y is equal to 0.525 multiplied by 2.75 plus 22. Evaluating that, we find that Y is equal to 23.44375. So how does that help us find the value of X, the actual answer to the problem? Well, remember that we constructed this Y using the property, the symmetry property of the normal distribution. So if the normal distribution is symmetric about the mean of 22, that means that this distance here between 22 and Y must be the same as this distance here between 22 and X. So if I figure out the difference here, I can take that difference to give me back to X. So let's take a look. Mu minus Y is equal to 22 minus 23.44375, which is minus 1.44375. So the distance between mu and y is 1.44375. I can then use that to tell me that x is equal to mu, or the mean, minus the distance, which is 22 minus 1.44375. And evaluating that one gives me that x is equal to 20.55625. Okay, so there we have the x value that's required to give us that the probability that our random variable is less than 20.55625 will be equal to a probability of 0.3. Okay, so that's just some of the types of inverse problems you can deal with when it comes to the normal distribution.